at a lot more examples because there are a lot of different cases that we can see. Up to now, we have found multiple cases in which the two eigenvectors had either one had a positive eigenvalue and one had a negative eigenvalue. This is called a saddle node. There are other cases. For example, let's look at this matrix. 2, 1, 3, 2. And we have x prime equal 2, 1, 3, 2 multiplied by x. We do the steps and we find that the eigenvalue is 2 plus or minus square root of 3. Then we do the steps to compute the eigenvectors, and we find that the eigenvector associated to 2 plus square root of 3 is 1 square root of 3. And the eigenvector associated with 2 minus square root of 3 is 1 minus square root of 3. So now, if we look at the general solution, we notice that both exponentials have a positive coefficient in front of the time. So they're both growing over time. But the first coefficient, 2 plus square root of 3, is growing faster. Square root of 3 is smaller than 2, so 2 minus square root of 3 is still positive, but it's much smaller than 2 plus square root of 3. So the first block, the first eigenvalue associated with the first eigenvector, grows faster than the second block. So when t is small or negative, then the second block is important. When t is big, the first block is important. So if we are going to be plotting it, again, we start by plotting the eigenvectors, v1 and v2. Then we stretch the eigenvectors to be full lines. And they're both moving away from the center. But we know that v1 is moving faster. Faster when t is big. Slower when t is small. So if you start at a certain point, it first moves along v2, that is the eigenvector associated with the slower eigenvalue, and then the other eigenvector catches up and starts pushing it in that direction. So we have something like this. First moving somewhat along v2, and then very fast going towards v1. If we plot everything else, we notice this stretch along the slow eigenvector. As soon as we move a bit away from that, very fast we go along the fast eigenvector. And let's have another example. We have minus 2, 1, 3, minus 2. X prime equals a times x. First step, again, we compute the eigenvalues, and we find the eigenvalues to be minus 2 plus or minus square root of 3, and we compute the eigenvectors. If we did the calculations exactly, the first eigenvector associated to the eigenvalue of minus 2 plus square root of 3 is 1 square root of 3, and the second eigenvector associated to the eigenvalue minus 2 minus square root of 3 is 1 minus square root of 3. So the general solution has again this structure of c1 times the first eigenvector multiplied by exponential of the first eigenvalue times time plus c2 second eigenvector exponential of second eigenvalue times t. But now they both decrease over time. What does that mean? It means that over time the rule solution tends to go to 0. But as we had before, we have one direction that goes at a different speed than the other one. So in particular, the first exponential, minus 2 plus square root of 3, is just barely negative, while the second eigenvalue, minus 2 minus square root of 3, it's in absolute value bigger. So this one decreases faster over time. As before, it means that when t is small, the first block is more important, because when t is small, that whole block is still there, while the other one is gonna draw towards the end. So it first starts decreasing in the first direction, and then it starts decreasing in the second direction. So for t big, the first block, I think I mixed it up a couple of things. For t big, the coefficient, the bigger negative coefficient disappeared faster. So for t big, the coefficient minus 2 plus square root of 3 is the one that is still there. So for t big, that means towards the end of our moving time, we're moving along the first eigenvector. While for t small, or negative, we're moving along the second eigenvector. That means that if we do the plotting, we plot the first eigenvector and the second eigenvector, we stretch them to be lines, we know all of them are moving towards 0. And for a point that is not on the eigenvector itself, if we start at any other point, for t small, we are moving in the same direction as the second eigenvector. For t big, we're moving as the first eigenvector. So what we see is something like this. And if we stretch that, we see something very similar to what we saw in the case of two positive eigenvalues, except that now we're moving everything towards the center. For t small, we move along the one with the eigenvector associated with the biggest negative, the absolute value biggest negative eigenvalue, and then we start moving like the other direction.